So today we're gonna start talking about something new, a new section of the course, which is global symmetries and local algebra. So this part is about, we talked about non-local observables in classical field theory, right? These were Wilson lines or Wilson loops. Wilson lines ended on pairs of charge, anti-charge, and Wilson loops. Now, we're going to talk about this in quantum theory, but from the perspective of local algebras. And for this lecture and the next lecture, we're going to be talking about that. For this lecture, the focus is on global symmetries and what they mean for local algebras. So we're not going to be using Lagrangians anymore. We're going to use local algebras for this lecture and the next. All right, so a quick review of what we discussed last time. We use background gauge fields method to compute one-loop beta functions of non-abelian gauge theory. We define covariant background field D'Alembertian. This is what it is. It's calculated or defined for any representation and any spin J. This is the representation of the internal symmetry, gauge symmetry, or of what your fermions are, for instance. And then this is the spin, so space-time symmetries. This is the background covariant derivative. Then you have the background field strength, which is sitting next to these. These are the gauge, the Lie algebra generators. And then here is the Lorentz generator for spin J. The determinants of these operators contribute to the one-loop effective action. If you recall from Fedorov-Popov, so we had one, which was delta of G, adjoint representation, spin 1. That had to do with gluons. We had one of these guys to the power of half, minus a half for the, that was, the gauge boson was that. Then we had this NF fermions for, this is half, and then this, if fermions are in fundamental representation, this would be N. And then we had the ghost anti-ghost, right? Which are in the adjoint representation and spin 0. All right. And what we did was that we took the effective action and we wrote it. We took these log determinants with the correct signs, depending on what the statistics is. We wrote it. Each of these guys, we extracted out of them the term that's proportional to the field strength squared, so that we could interpret that as a renormalization of the coupling. Of course, this renormalization is divergent, log divergent, so we have to do renormalized perturbation theory, but we did use a quick trick, which was basically using a thin shell momentum integral, and this was the answer that we found. These are basically the definitions that I have, and then C stars were just fixed by quantum numbers, right? So basically this is all kinematics. All right. So the result of this was the beta function is G cubed over 4 pi squared. This is the T of G. So hopefully you recall what that is. Minus 11 over 3 TR, the fermions. This is the gauge boson adjoint. NF minus 4 over 3. Putting all of this together, we found that because in a pure Yang-Mills theory, NF is 0, so beta functions are negative. Then for any particular, say SUN, Tn is half, right? So this would be half, and then this guy is Tn is this guy. Tn is SUN, right? SUN gauge theory. That's N. Tr is half, right? That's right. Sorry, I think I wrote this incorrectly. Anyway, so but the outcome is that for any SUN fixed N, there is a maximum number of fermions that will keep, because fermions are screening, gauge boson is anti-screening still wins, right? And then the theory is UV finite, or as we call it, asymptotically free. So in an asymptotically free theory, this is what it looks like, what the beta function looks like. at one loop minus g cubed 4 pi squared b, be some positive number. It's convenient to repackage it in terms of g squared. This way, you see that alpha, which is the coupling of the theory at scale mu, compared to some other scale, m, is related to using this equation. It's just a rewriting, right? Integrated version of it. Then we saw that there's a Landau pole. There's a Landau pole. So m is, say, some higher energy scale. Mu is a smaller scale, or how do I want to do that, actually? Yeah, that's right. Mu is a smaller scale. M is a larger scale. So this is negative. When this satisfies this equation, right? When m and mu satisfy this equation, you have a Landau pole. This means that basically deep in the infrared, you expect the coupling to blow up and the theory is strongly coupled. Your description of the theory collapses. We don't know what happens. In the case of QCD, or non-abelian gauge theory, the belief is that the theory confines, right? Now, what is confinement? What do we mean by saying the theory confines? A gauge theory is confining if all finite energy states are invariant under a global underscore gauge transformation. That means that this is a symmetry, right? If this is to be a symmetry, it means that you can never excite a single quark, a single any particle that is charged under the non-abelian gauge. You can never excite such a thing. Physically, it means that the energy cost of that thing, of course, depends on the coupling, and as the coupling is gone to infinity, the energy cost is infinite. This is the physical description of it. So what are the finite energy excitations? There are quark-antiquark pairs that are connected by Wilson lines. That thing is gauge invariant, right? Or you could have Wilson loops, right? Wilson loops could be in space. If you have a Wilson loop in time, the description of it is like this quark-antiquark pairs, right? At some point, you pair create them, right? So once they are pair created them, this is what the state looks like, right? Quark-antiquark. You evolve in time and then reannihilate, right? So that will form a Wilson loop in time. And what happens if you try to separate them? If the potential is linear. You have a question?
Yeah, so you derive the Landau formula using perturbation theory.
Yeah.
A non-perturbative description of this, would that Landau formula disappear? Or?
No, in a non-perturbative description, what will happen? Well, depends what you mean by non-perturbative description. What happens is that as the coupling grows, so Landau pole is just something that you see that Landau pole is when you calculate beta function perturbation theory, and you see that naively at some finite energy scale, whether it's UV or infrared, the coupling blows up. This is a sign that perturbation theory is going to break down. This is a signature of the breakdown of the perturbation theory. What does that mean for physics? It means that if you are to build an EFT at lower energy scales, the degrees of freedom that are going to be described, being that theory, EFT, are not going to look like your quarks and gluons. So you need a brand new EFT. In the case of QCD, that's a pion theory, right? The theory of pions. But in principle, a priori, you don't really know what happens. That's just a sign of what, like you don't really know what happens. Yeah. If you try to separate these in confining theory, their potential that corresponds to these two guys, right, is scaled linearly, right, with their separation, which means that to isolate a single charge, it will cost infinite energy, right? And that is related to the fact that, of course, you can never isolate, you can never have a single charge. But then what happens, you could ask physically, what happens as you separate these two guys? If this were particle theory, not many particle physics, many particle theory, you have a Fock space, this is an interacting theory, their description would have been that as you separate these guys, it just costs more and more energy. However, QFT1, lecture 1 or 2, we discussed that in a relativistic theory, the moment you have enough energy to create a pair of particles, the theory will pair produce. So this is what's going to happen. This is the physics of what's going to happen. All right. Questions? All right. So to motivate, we said that the expectation value of a Wilson loop that is in time is actually in Euclidean time is an order parameter for the confinement deconfinement phase transition. So at the moment we have no argument to even argue for the existence of a phase transition. But if the theory confines, what should happen is that your description deep in the UV is in terms of fundamental degrees of freedom that are quarks, and then those degrees of freedom become infinitely heavy. You have other degrees of freedom. You've undergone a confinement deconfinement phase transition, right? And how do you tell which phase you are in? We often, Landau taught us that the way that we do this, in simple cases, when it's not topological order, we use local operators called order parameters. And here is an order parameter. It's not local, but it's a Wilson loop in Euclidean time that I'm calculating. Now, why is this an order parameter? We said in Euclidean time, if capital T is much larger than R, this is just e to minus t, the energy of the pair. And when we calculate this expression in perturbation theory, for example, in QED or a QCD, non-abelian in QED, we could calculate this exactly, but in non-abelian gauge theory, you have to do approximations because it's interacting. You find a Coulomb law behavior, right? So the energy of the pair, there will be a UV divergence, and then the Coulomb law tells you about this operation. In a confining phase, what you find is something that scales with distance. All right. Then we talked about Wilson loops at infinite coupling. We said, well, okay, now that the description of the theory, in perturbative description of the theory, QFT falls apart, what can we do? The only thing we can do really is to put the theory on a lattice, right? And do explicit path integrals somehow using Monte Carlo and numerics somehow, right? Well, Monte Carlo is numerics. So to recall how we made sense of gauge theory, non-abelian gauge theory and lattice, we took a lattice. On each link, we put an, say we're doing SUN, we put an SUN matrix element, right? Say BX alpha. And then we're labeling the link by the endpoint and also a direction. Why a direction? Because this is a connection, right? And the connection is not abelian, it's going this way and coming back. Coming back would be the dagger of that unitary, right? Okay. Now, what happens is the following. When G goes to infinity, well, okay, so then we wrote down the action for this. That whole, do you recall what the action for this was? It was a sum over all plaquettes, right? So for each plaquette, you multiply this guy by this guy by this guy by this guy, and take a trace, and you sum over all plaquettes, traversing plaquettes this way and the opposite way. Why? Because this is the Hermitian conjugate. Because you want your action to be real. And when you add these two, the fact that F mu squared piece, this is a nice exercise to do, comes from the fact that you're taking both of them, you're adding both of them. Okay. All right. So now there is an action. 1 over G squared sits in front of it. When G goes to infinity, what it means is that the action goes to 0. So in the path integral, each path was the weight of each path was something like this. So the weight of the path becomes 1. It means that all path or field configurations are equally likely. What are the degrees of freedom you're path integrating over these unitaries, these gauge fields? You have to path integrate over the unitaries with uniform measure. Such a thing is called Haar random integral. And you're going to be doing a bunch of Haar random integral in your homework. And the result of those integrals is this lesson that you learn is that when you calculate this guy, this Wilson loop, what you find is that it goes like the area of the Wilson loop divided by epsilon UV squared. And that area is T times distance. So you conclude that in the confined phase, E pair is proportional to distance. the area law is important, right? So in the confined phase, the value of the one-point function of the Wilson loop scales like the area law. That is the important lesson, right? Questions? This is the summary of what we discussed last time. It's a good moment to pause and ask questions, because what I'm going to do going forward is completely change the topic.
Those unitaries that you talk about are just the comparators. Well,
Or what?
Are the comparators, what basically calls the comparators.
To compare, they are the connections.
Yeah.
They're the connections, right? They're the also lines, if you wish. Good. All right. Yeah.
I don't know if it's a silly question, but so like in the proton, there's a non-zero spin associated with it. There's obviously non-parametric dynamics taking place
Within a proton. So okay, so that's a bound state of 3 quarks.
Yeah. So I would think naively that if I take the limit of infinite coupling for an unpolarized proton, I would see the proton constituents that maybe are averaging out. Like, is it enough to say that there is like the emergence of a spin of a proton is just the fact that it's not infinite. There is some.
No, sorry. There's a whole bunch of things here.
Yeah.
So there is, okay, the fact that you have confinement means that you're not going to get individual quarks out.
Yeah.
You're going to get bound states of the quark, which are, at the moment, we say them SU3, right? In the case of QCD, invariant. Okay. Right? Now, those guys could come out of pairs of quark antiquarks, right? Mesons, or they could come out of baryons, right? Now, at the level of this argument, a priori, it's not at all clear when mesons come out, when baryons come out.
Sure.
Right? So this is the EFT. You write down an EFT, and that EFT is described, and what we call baryon is about actually what is the charge, what's the charge under SU3 times SU2 times U1, right? Mm-hmm. So we'll get to Stanwall and discuss it. But the question of what is a proton made out of is a deeply non-perturbative question.
Yeah, that's kind of what I'm trying to understand here, is that like it seems like an infinite limit coupling, it becomes almost trivial, right? Because it's equal paths, all the paths are equally likely. It
is very, it trivializes the story, right? So okay, maybe what you're asking is the following. Indeed, the infinite coupling limit trivializes the theory. Yeah. Then, if you want to look into the confinement dynamics, what you would like is a perturbation theory around infinite coupling. There exists such a thing, and it has some phenomenological success. I don't know much about it. I don't know, but there is such a thing, and that would capture the fact that the couplings are not literal infinite, because infinite coupling doesn't quite make sense, right? It's not quite infinite, but it's large, right? Now, the infinite coupling perturbation theory captures various things, but it's well beyond my, I don't know much about it. Yeah, for sure. All right. Any other questions? Now we're going to change gears and completely change gears and talk about non-local observables in quantum field. All right. In quantum field theory 1, we saw that stable particles, I think in retrospect, this section should have been before the beta functions of SUN, blah, 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 but there's a little bit of discontinuity. So there's a sharp transition. I apologize about that. In quantum field theory, we saw that stable particles were irreducible representations of Poincare group labeled by mass and spin, JNS. Right? That was in our discussion of quantum field theory. That's what we call a stable particle. Then unstable particles were resonances. Right? We discussed that as well, but that's not our discussion today. When we have charges, we end up with reducible representations. This is one of the points I'm going to make in these two lectures. And every time you have reducible representations, the physics terminology is super selection sectors. This is a familiar phenomenon. You already know about this, but I'm going to use this to introduce this terminology, and I'll give you a different perspective. Okay, so is it clear what we're discussing? We talked about charged particles. We talked about stable particles as being irreducible representations. There are particles, if you have symmetries, the particles that you're talking about actually are often, you could talk about reducible representations. They naturally appear, and we're going to discuss that. And that's in the context of the so-called theory of superselection sectors. All right, it's very intuitive. We'll discuss that. Now, I won't have time to do justice to this, but the way to think about this, the modern picture that I want to advocate is the following. Every time you have charges or symmetry transformations, you have the algebra of charge neutral observables, which is a sub-algebra of all operators, including charge fields, right? So this is one terminology that I'll try to clarify, but that should be a little bit familiar. There is something called R4 symmetries. You know, this sort of symmetries, global or gauge, all of that. In this discussion, they're all going to be all packaged together as R-form symmetries. And then there is another thing that's called additivity and Hog's duality that I'll discuss today. These are all related. These are all various ways of thinking about the same thing. So up until now, we've talked about symmetries from the Lagrangian perspective. These two things are a local physics perspective on symmetries. And they actually shed light on some new aspects of things. So for instance, you will see that every time you have charges, gauge theory or global symmetry, you have non-local operators. And these non-local operators always come at a cost that you end up with super selection sectors. So this is what we're going to go over. Is the plan clear? I will not be able to do justice because we have only 2 lectures. But today I'm going to discuss this part. And this triangle is for you to be guided if you want to go and study more about this. Good? Questions? All right. Let's start with global symmetries. Today, everything I'll say for the remaining of the talk is global symmetries, otherwise known as a zero-form symmetry. Doesn't really matter. That terminology doesn't matter for today. It will be for the next lecture. Let's start with global symmetries. The simplest symmetry, global symmetry that I'm going to consider is the space-time symmetry. What is the story? If you have an integer spin particle, if you rotate by 2 pi, your operator comes back, your wave functions come back to where they were. If you have a half integer particle, what you have is an irreducible representation of the double cover, right? Well, actually a projective representation of it. And what it means is that you have a Z2 symmetry transformation. Rotation by 2 pi will send bosons to bosons, send fermions to minus fermions. Sorry, spin half. You know. So the Z2 is that the rotation by 2 pi squares to identity. Rotation by 4 pi will bring everything back. If the operator is spin integer, is invariant under it. If it's spin half integer, oops, sorry about that. Half integer, then it picks up a minus sign. So for example, a fermion will pick up a minus sign. This is a local transformation. This might confuse you. A global symmetry is a transformation that you could do at every point. Okay? Good. Now, rotation by 2 pi will not bring your fermion back to where it was. It will give you a minus sign, it means that a fermion is not an observable, it's a field. There is no way on Earth you have an observable and you rotate things by 2 pi and you pick up a sign. That makes no sense. Right? This is some terminology. So from the point of view of the Z2 symmetry, what are observables? They are charge neutral operators. Right? So invariant operators of the under symmetry transformation. Charge is the log of it. Here's Z2, so it doesn't really make much sense, right? So, but invariant operators. From the point of view of the Z2 spinner, spin half particle is charged. It transforms instead of. So what is the transformation? Can you tell what the transformation is? Anyone?
The particles,
Do you know what the transformation is? So, what O? It's O e to the power of I pi, right? You could think of this as what here? Number of fermions, right? Or said differently, is we sometimes write it this way: -1 to the number of fermions. Sometimes write it as NF. So even and odd are two different things. The ones that are odd are observable. The ones that are not odd, well, odd or even, we call all of them fields. The ones that are odd even are observables. I warn you, this discussion to people who have not dealt with operator algebras, if you talk to them, they might get confused and get mad at you. However, this is for you to know, this is an alternative way of presenting stuff. This is very modern and it's led to a lot of recent developments. So this is not part of like textbook material unless you're an operator algebra person. Okay. Yeah.
What would they take issue with?
It's just that they would a typical physicist would say, oh, a fermion is an observable or a field is an observable. It's just loose language, right? It's imprecise language. But here we are being very rigorous, and the reason is that historically, when mathematical physicists were rigorous about this, and physicists in the 70s, 60s, and 70s, physicists looked at their results and they never saw that this language is adding anything. But these modern developments have taught us that actually it adds something. What does it add? It gives a unified picture for global symmetry, gauge theories, and generalized symmetries. This was the new thing. And back then, there was less appreciation for general. Well, people didn't know about generalized symmetries, at least in modern language. All right? Okay. Now, if U is a unitary in the Hilbert space, right? So transformation symmetries are realized as unitaries or anti-unitaries. In this case, it's a unitary. It's representing rotation by 2 pi. The vacuum of the theory is with no excitations. Bosonic or fermionic is invariant under it. If you take a fermion and act with a fermion operator on the vacuum, that creates a fermion. That is a one fermion state is not invariant under it. How do you show that? Well, this is U acting on psi. Insert U dagger here. U leaves this guy invariant. This is minus psi, so you pick up minus psi. But this is okay. This was exactly in quantum mechanics. Why we said in quantum mechanics, we don't necessarily need a representation. We need a representation of the universal cover or projective representation. Because vectors are allowed to, up to an overall phase, things are allowed to change. Right? Why are they allowed to change? Because when you stick them inside expectation values, some operator, U dagger, acting in the vacuum, these are invariant, that's good. And in some excited state, This will give you a minus sign. This will give you a minus sign. The whole thing cancels, so it's invariant. But this means that you should always talk about states that have a pair of fermions, right? This looks like a pair of fermions. Can you see where I'm going with this?
You're gonna have seen the excitation.
That is correct. However, I'm trying to make another point. This is when we talk about super selection sectors, this is exactly where it comes from. Okay? So here's what it is. Imagine you take the vacuum and write down a superposition of a vacuum state and a state with a single fermion. Okay? Now, if you take this state and you think you take this literally as the state that exists, put an observable in the middle and calculate the expectation value. You'll get these two terms, right? But you would get these two terms. It means that under a unitary transformation, the expectation values of this guy under rotation by 2 pi do not come back to where they were. That's physically nonsense, right? There can't possibly be these guys. And it's just the same, and if you look at this, this looks like an overlap of a single fermion state with a state lab. So what do you conclude? From this, you conclude states with different fermion numbers or states with different charges, quantum numbers that are charges, cannot be superposed. There is absolutely no physical meaning to superposing the vacuum state plus a state with a single fermion. Simply because that state is not invariant under rotation by 2 pi. That's just pure mathematical fantasy. What makes sense? If you look at this, there's this term and this term. These two looks like a mixed state. It's actually this mixed state. So all you have instead of superposition is that you could have statistical mixtures. How do we describe that in physics? In math, super selection sectors, precisely super selection sectors. So what do we say? We say there is a Hilbert space on top of the vacuum that is built out of the action of, I'm not writing these. These are all the charge neutral operators. Neutral operators, so let's call them A, acting on the vacuum. Then there is another sector of the theory, I'm going to write it side. Same operators, A acting on a single fermion. These are two different sectors of the theory. The Hilbert space is H omega plus H psi. So far, so good. Direct sum. And if you look at operators, if this is the part that is H omega, this is the part that's H psi. To say that there exists no meaning to superposing them, it means that operators are always like this. And anything with a non-zero thing here will act on the vacuum and create a particle, a single fermion, or vice versa. That's not allowed. So in physics, if you have in mathematics or physics, if you have an algebra, another algebra, when you direct sum them, it means that you put zeros here. You don't allow for anything else. That's what the theory. That's what we mean by super selection sectors, right? So, but the point, the physical point I want you to know is that it makes absolutely no sense to try to superpose two vectors from different sectors. That's mathematical nonsense. Physically, then it just means a mixture. Good? Good.
Say we have momentum conservation in our system, but we talk about like adding momentum, superposing momentum states all the time. So what's the issue?
We'll get there. We'll get there. These are so. What your space-time transformation? Okay, sorry. Let me try to say it a little bit differently. Keep that question in mind. We'll get there. This is the issue of right now. We're discussing internal symmetries. right? I'm doing this even though it's space-time, but I can do it locally. What do I mean by that? I mean that I can take space-time. We'll see that in a second. Take this stuff here, and only to these guys I can apply unitary rotation, or vice versa, right? So I can do this at different points in space-time. Whereas that setup is a little bit different. Those are technically, it's a question of algebraically we call them. We talked about endomorphisms of the algebra. That is not an endomorphism. Blah blah blah. I'm hiding some mathematics, but think of things that can act locally. So, yeah, the Hilbert space is the direct sum of the vacuum sector and the one fermion sector, or said differently, it's the direct sum of the sector with an even number of fermions and odd number of fermions. This is a reducible representation. Hopefully that's clear, right? What are the charge neutral operators? They're the observables. They must be bilocals or four locals or 2n locals. They're generated by bilocal operators like this, right? These are familiar, right? Psi x, psi y. What does it mean? You created the charge here and then negative charge. So pairs. So your constraint is that the total charge has to be 0. That's okay. You could have these guys, but these are non-local operators. Can you see why they're non-local? Because they cannot be generated locally. This is, you write it as psi x, psi y, but psi x is not an observable. So, is it clear? We use the field algebra because we want to generate everything locally. This should resonate with gauge theory. In gauge theory, we had these Wilson loops. They were non-local operators. We wanted to insist on a local description of it, generate them locally. So we invented these unphysical degrees of freedom called gauge fields that has certain transformations. We could never observe them, but they were related to our observables. This is similar to that. That's gauge theory. This is global symmetry. Next lecture, we'll take the extra step of relating. But for now, this is an analogy, okay? All right. So we'll use this terminology of psi. We're going to call it field, and then the bilocals or bilocal things, or the things that have under -1 to the power of f, fermion number is even. They're going to be local physical charge neutral observables. Actually, if you want physicists to never argue with you about the word observable, sometimes physicists get mad. That's just terminology that's common in this language, in this literature. The only thing that they would take issue with is the word observable. You can always talk about charge neutral operators and charge operators. That's fine. In this language, in this terminology, fields are all of them, and observables are charge neutral. But you don't. That's just the only thing that historically people take issue with. All right, good. Running really. Oh, I started late, so good. Now, I'm gonna remind you, or maybe tell you a little bit about local algebra of quantum field, local algebras of quantum field theory. So here's an important thing. How did we describe symmetries up until now? We talked about charges. These had to do with intervals over codimension 1 surfaces of currents. This is a global description. It's a very, very global description. The current was conserved locally, but we're always talking about these charges. The charges are something global. What we want to do is I want to have a theory that I could discuss. It's basically equivalent to the same thing, but I want to just say my laboratory is this room, and I can't care less about what goes on in the Andromeda galaxy. I just want to know whether I have a symmetry in my theory just using the things here, right? I want to do things locally. That's the word local algebra. You know, the formalism of quantum field theory, formulation of quantum field theory up until here, the Lagrangian base approach has been about S matrices. Those are the things you observe all the way out at infinity. You collide a bunch of things and things come out, right? That's a very global perspective. This is a local perspective. Okay. Now, just to remind you how things work, consider in space-time, consider a region which is an open set, for example. Sub-region like this. There is the field operator. I'll be careful with my terminology. Field operator. Take the field operator that points that are inside this and integrate it against a kernel. That is an operator. This kernel, because it smooths out in time, it will regulate the divergences, blah, blah, blah. This operator is still unbounded. You could exponentiate it, a whole song and dance, and then you could make sense of this as a bunch of bounded operators. But I don't want to focus too much on that. But this is an operator. If this is like a simple theory without any particular symmetries, this is an observable. So you have the vacuum of the theory. What are the excitations? If you act with this operator on the vacuum, that's a local excitation. At least that's clear from the free field theory, right? In free field theory, this literally creates a particle here, right? Or a superposition of it somewhere here with some coefficients. These are excitations. So act with one of them, act with two of them, three of them, all. What's the Hilbert space? The Hilbert space is you take all of these guys, you act on the vacuum, and take the closure of it. That's the Hilbert space. Now, you might wonder if you just take all your operators from A and take the closure, maybe that's a Hilbert space that depends on A. There's a theorem in quantum field theory called Riesch-Schlitter that tells you that, nope, this thing is the whole thing. That should be shocking, but it's a fact. And we're not discussing that for now. It's just a whole thing. But let's not worry about that aspect. Okay? So I just pick these guys and I can talk about the Hilbert space. I'm setting the stage to make a sharp point. If there are any questions, ask. Now, for a second, forget about algebras. Let's talk about space-time and regions. Given a region space-time, we are going to define a causal complement for it. The causal complement of a set A, open set A, is the set of all points y such that the proper distance between y and all points in x is positive. For example, if this is A prime is this region. It's uniquely fixed in any space-time that's causally complete. It's uniquely fixed. Given a region, there's a causal complement. Good? Now, to an algebra, there also exists a similar notion. So here we associated to A an algebra of A. So think of quantum field theory as a map from regions to algebras, right? Now, there is a similar property, the similar relation called the commutant. Commutant is the set of all operators on the Hilbert space that commute with all observables that are related to this region. Now, causality tells you that something that's causally disconnected must commute with all operators in it. So it means that the algebra of the causal complement is inside the commutant. Good. The question that we're going to talk about is that could it be equal? You're good? You're with me? So, of course, at this level, there is no chance of it being equal. I'll build up. But I just want to understand, I just want to make sure that everyone is clear about this. Quantum field theory is a map from regions in space-time, open sets in space-time, to algebras. And it's going to have, this map is going to be structure preserving, meaning that there are a bunch of relations and properties that regions in space-time have that we would like that to also transfer faithfully to properties of algebras. We would like causal complement to go to commutant. That's something desirable. So, first thing you notice is the following. Now I'm talking only regions. Take this region. Oops. Take this region. What is the causal complement of this region? is this thing. What is the double causal complement? The causal complement of its causal complement is all this region. Okay. Now, because of this, A triple is equal to A prime. A triple prime is equal to A prime. Do you see that? So it means that I'm going to define a region causal complete if it's equal to its double causal complement. What are such regions? Double cones, wedges. Now I kind of stand the chance of actually having some nice properties.
That's why the causal diamonds are so favorable.
Good? Everybody's with me? We call such regions causally complete. What is the algebra of the causal complement? Well, again, causality tells you that, well, the algebra of the causal complement, do you have a guess what would be desirable to associate to the algebra of the causal complement? So we just define the causal complement of A to be this region. What is desirable to be the algebra of the causal, given this algebra? What's the algebra of this? The desirable thing is that it would be double commutant. Because if prime goes to prime, if causal complement goes to commutant, you would take the commutant of the commutant. So here we define the causally complete region. It's natural to define an algebra. Consider algebras that are equal to their double commutants. What are those algebras called? They're called von Neumann algebras. That's the very definition of von Neumann algebra. Von Neumann algebra is an algebra which is equal to its double commutant. It closely mimics this property of a causal complete region. There's a sense in which von Neumann algebras are complete, commutant complete, if you wish. They're commutant complete. Good? Now, this is a little bit of an advanced comment, but anyway, in quantum field theory, we have a map from space-time regions to algebras. Regions go to subalgebras. These are subalgebras. Causal complement goes to commutant. Causally complete regions go to von Neumann algebras. To causally complete regions, we associate von Neumann algebras. Now, what mathematicians say a net of causally complete regions go to a net of von Neumann algebras. I don't want to describe what a net is. Okay? So far, so good? Let me give you a little bit more information about this. What I mean by net. You would like this map for this map to, so this was a quantum field theory, but you want quantum field theory to be local. I'm going to give you a definition of local quantum field theory. How did I define local quantum field theory using Lagrangians? I said I've done Lagrangian functions. But then we saw under the RG that was kind of wacky. If the theory was asymptotically free, it was okay. Sometimes it's not okay. I don't want to do any of those. How do I define locality? How do I describe locality in terms of these algebras? Here are all the criteria. Inclusion. There is a notion of inclusion for algebras. Subalgebra. So if a region is inside another region, right? Now I'm talking only causal complete regions, say for example wedges or double cones. Right? If this is inside B, the algebra associated to this is a subalgebra of that. So that's what we would like. It's called nesting. You would like covariance to be true. It means that if you have a transformation that translates this region, the symmetry, to this region, then there is a unitary on the Hilbert space that takes this algebra and sends this algebra. So symmetry transformations are represented unitarily in the Hilbert space. Finally, it's desirable to have what's called Hog's duality. That it's true that the algebra of the causal complement is inside the commutant, but we would like this to be equal to the commutant. Yeah.
What does it mean if you have other things besides the?
What do you mean other things?
Like you would like it to be equal, but
I'll give examples. You'll see when you have charges, it's never going to be true. When this is true, we say a quantum field theory is complete. systems with charges, systems with symmetries do not have complete algebras. We're going to say that in a second. Good. Now, a fact about relativistic quantum field theory, I will not have time to prove it, it's complicated, is that this is true for topologically trivial regions that are causally complete in quantum field theory, such as double cones and wedges. In particular, the proof for wedges is very old, from the 60s. So that's why Hogg is here. Right. Good. But think of Hogg's duality as a strong form of causality, because this being inside that was causality. Being equal is saying that it's stronger than that, right? But here's a warning. The fact that this does not mean the following, that if two operators commute, this is inside A prime. It means that if there's an operator OY that commutes with everything in this algebra, it could be equivalently represented here, but it need not be literally there. This is a subtle thing. For example, if you're curious, just work this example. Take massless free fields. Massless free fields in 1+1 dimensions. If you take the commutator of this is time and this is space, if you take the commutator of two operators, scalar phi x and phi y, phi x1, phi x2, the commutator of these guys is 0 when they're space-like separated. It's also 0 when they're time-like separated. Why? Because the theory is massless. When you make this perturbation, things propagate, the effect propagates with speed of light and no other speeds. This cannot affect that. Only massless theory, massless fields. So now this commutes with this, right? So we might be saying that, oh, so this is region A, this is A prime, but this is not in A prime. That's okay with Hogg's duality. It means that this operator could be equivalently represented in terms of things only here. And that's okay. In physics, when you have an operator at this point, evolved in time, it could be that same operator later on could be equivalently represented here. Right? Because the time there's Hamiltonian. Hamiltonian evolves things. Good?
That's similar to what Jonathan did just of evolving the scalar field with the
All right. You're with me? Okay. So now, I said all of this. What are we going to talk about? We're going to talk about Hogg's duality for systems with charges. In particular, the simple example of the Z2 fermion thing. Okay? And I'm going to be in 2+1 dimensions for a particular technical reason that will become clear. It doesn't have to be 2+1. But 2+1 is clear because I can draw things nicely. So take a theory of fermions, free fermions for simplicity. In 2+1 doesn't have to be free. To every causal complete region, the causal diamond, I associate an algebra of observables. These algebras are always bilocals, generated by bilocals, so 2n locals. Good. Here's the commutant. Here's the region. To make my diagram simpler, I'm just going to draw a constant time slice picture. So this is A and this is A prime. Good. For this A and A prime, I told you already, there's a proof that Hogg's duality holds. So the non-trivial case is when you talk about regions that are not simply connected. A1, A2. Good. Now we want to know, could the algebra of A1, A2 prime be equal to the algebra of A1, 2 prime? This guy. Everyone's with me? How, if we find that this is not true, can you identify what the origin is? What can make this fail? No, not really. If you have a non-local operator, that's not non-local operator here, that's not generated using these two guys, that'll make this correspondence fail. We'll see that in a second. So what this is exactly capturing locality. Do you know that the setup clear? Is the setup clear? Okay. So all right. So everyone knows what duality is, Hog's duality. I'm going to introduce another terminology, additivity. And these are the only two things I need to worry about. Additivity is the following statement. It's something that you wouldn't even think about just as an assumption. You would just say for sure it's true. It says the algebra of A1, A2 is generated by the algebra of A1 and A2. Okay? It means what? The algebra of A1 was generated by these bilocals. The algebra of A2 was generated by these bilocals. So you just put them together. Mathematically, we write this sign. It just means that this algebra is generated by these two guys. Yeah?
Is that like a direct sum? Like if I want to visualize it,
it's tensor product. It's more like tensor product. Good. But now here's an issue. You could have a psi here and psi here. This is a bilocal that is neither, that's not generated by, is not in here. So there is a charge neutral operator that's supported in here and here, but you cannot generate it locally. Good. This is a genuinely non-local operator. The way to generate it locally, to introduce this field, which is non-observable, now you could generate it locally. Again, think about the analogy with gauge theory. You have a non-local operator, Q minus Q, and there is no such a thing as an operator that creates charge. But if you do assume such a thing, you could generate this locally, so you're good. These operators, I apologize, the language for them is intertwiners. I'm not going to explain why. They're called intertwiners. This comes from mathematical terminology of representation theory. There's a term in representation theory for this called intertwiners. But think of them as bilocal charge, anti-charge. Good? You're with me? Good. Now, what is the algebra of A prime? Well, you would say the A prime is kind of simple. You say the algebra of A prime is just bilocals Z1, Z2s like this. Good. Take the algebra A1, this A prime. So here are these guys. What is the commutant of this algebra? This non-local charge anti-charge commutes with this. Is it clear why? It does commute with it. So what do you find? You find that if you define the algebra of A1, A2 as the additive algebra, duality fails. The commutant of this shaded region has something beyond what could be generated here and here. It has this bilocal operator. So duality will fail every time you have global symmetries. Good. This is, let's use this notation, IXY. So then you might say, oh, I'm going to fix duality. How are you going to fix it? You say, well, I'm, so I stuck to additivity. I saw duality fails. I don't like that. Let's just let go of additivity and make Hog's duality work. You can do that. Define the algebra of A12 as A12 prime prime. You just by definition do that. And what does that mean? What that means is that you define a maximal algebra associated to these two regions. Why is it maximal? Because, well, it has to be maximal. It has something on top of the additive. So this way additivity fails, but Hog's duality is good. But have you actually succeeded? No. Because you only checked it for this guy. You have to check it for the other guy as well. There is another funny operator here. To see this operator, take the additive algebra of these two guys and look at this commutant. In particular, look at rotation by 2 pi only on A1. Good. Rotation by 2 pi only on A1 commutes with the additive algebra of A1 and 2. That should be obvious. But it does not commute. It does not commute with the well, actually, here I'm actually saying it a little bit. I'm not even there. I'm saying that, so this commutes with A1, it commutes with A2, right? It also commutes with the algebra of A1, A2 prime. It also commutes with that. Good? Okay. So this tau, you can think of it, as I said before, -1 to the power of F fermion number, but fermion number inside A1. It's the observable, just counts the number of fermions there. It commutes with A1, A2. Good? So this tau is definitely in the commutant of the additive algebra of A1, A2. All right. So here it is. Sorry. Here's the additive algebra. You add it to this bilocal. You made Hog's duality work. You could add this operator called twist to the local algebra of AB prime to make Hog's duality here work. But you could only do one of them. You cannot do both of them. Why? Because the twist and this two charge thing do not commute. It's easy to see. Take the two charge thing. X is supported on A, so you push this through, you pick a minus sign. Y is A1, sorry. Y is outside of A1, so you could just push it, bring back, and these two guys do not commute. So you cannot restore duality by enlarging both of them. One of them gets messed up. First of all, if you stick to additivity, in the presence of charges, duality goes to hell. You could recover duality by letting go of additivity, but always, if you do that, the duality for the complementary, the causal complement region goes to hell. Okay, so in summary, I ran out of time. Here is what I want to say. Today, we talked about an aspect of global symmetry that could be detected locally. I never talked about charge operators that are coming from integrating something over the whole space-time, co-dimension one surfaces. I'm just looking at little things locally, and I'm diagnosing whether I have symmetries or not. And here, global symmetry has to do with the existence of this genuinely non-local operator, meaning they could not be generated locally. I can generate it locally if I insist on fields, but fields are not observables. Now, the reason that a lot of physicists get upset about this is that locality is so inherently inside us, so important for us that we don't even think about this step of insisting on something local, right? Field is for us is so important. Right? It's like, of course like that. But there's no distinction between this, as you'll see in the next lecture, and gauge theory. When we insist on introducing gauge fields, it's as fictional as this guy is. It's because we're insisting on local description. Now, the algebra of the fields is both additive and satisfies duality. Right? If a theory has these properties, it satisfies all duality for arbitrary regions and satisfies additivity, such a theory is called complete. We're going to see that, well, I'm going to say in a second, a complete theory has no charges, gauge theory or not. Okay. just to give you a little bit of a picture where we're going to go with this. So it talks about regions that are disjoint. Given a region, is there a topological quantity that counts the number of disjoint regions of it? So this is the zeroth homotopy group. This is something that counts. Now, if you have a region that has, so what we saw is that in gauge theory, in global symmetry, if you pick a region that has a non-trivial zero homotopy group, that's just fancy way of saying several disjoint regions, there will be non-local operators. Good. Such a theory is said to have a zero form symmetry, aka global symmetry. Can you generalize? What's the theory with a one form symmetry? It's a theory that if you look at a region that has a non-trivial homotopy group 1, otherwise known as fundamental group, then you end up with brand new non-local degrees of freedom operators. What is a region, and say 2 plus 1 of 2 dimensions that has non-trivial pi 1? Sorry? Just a sub-region in flat space. An annulus. Can you tell what the non-local operator is? A Wilson loop. Why? Because if you split this into 2 topologically trivial regions, this Wilson loop cannot be generated by the algebra of Wilson loops of this and Wilson loops of that. Now, what is an R-form symmetry? This is called generalized symmetry. It's a theory. A theory has R-form symmetry. If you pick a region that has non-trivial pi r, you come up with brand new. You will have brand new observables. Every time you have one of these are like the analogs of intertwiners, right? These bilocal things that we saw. There's an analog of the dual object. The twist was dual of the intertwiner. The intertwiner was the failure of the additivity for this region, and it has to be failure of causality. Failure of causality for this region. The failure, duality. The failure of duality for this region. The failure of duality for the complementary region had to do with the twist operator. So in that sense, they're dual to each other. Here is nothing but electromagnetic duality. So there's the Wilson lines and then the dual object. We're gonna be talking about those.
Where can we see this element in text?
This is very modern. I'll talk about this next lecture. It's like very, very recent. Well, I mean, it was sort of understood in the old literature, but there's a comeback of these ideas in the past 5 years. But it's so basic, it's so fundamental. I think this should be and will be a textbook material in a couple of years. Anyway, any last questions? I have to run now.
You're going to be there.
Sorry?
No, the thing is that I'm really intrigued to do the belly thing.
Okay. Even now? Let me. Any questions about the lecture? If not, let's just wrap this up. Now I can tell you about the